Today we'll continue looking at functions by discussing in more detail the domain and range. Our objectives for today will be to determine the domain and range of a function made up of ordered pairs, to determine the domain and range of a linear function, to determine the domain of a nonlinear function, and to estimate the domain and range of a function from a graph. Let's begin with the domain and range of a set with ordered pairs. This one you should be able to do pretty straightforwardly because we've looked at this before. If I give you this set and I ask you to determine the domain for me, you should remember that you need to pick out the x values. So I see a 2, a 4, a -5, and a 9. Those would be in my domain. Now we need to talk about the range. If I want to pick out the range elements, I look for the y values. I see a 7, an 8, a 6, and a -5. So those items would go into my range. I think you should be familiar with this already. There seems to be nothing new here. Let's continue now and let's look at the domain and range of a linear function. This time I'll give you a function f of x is equal to 3x plus 2. To determine the domain of this function, what we need to ask ourselves is this: what are the values that are legal for me to plug in to this function? Is there any number that when I plug it in, it causes the function to become undefined? So let's look at that. Let me take you through my thought process for doing this. Normally I would ask myself, what happens when I plug in a 0? Well, in this case, if I plugged in 0, I would get 3 times 0 plus 2, which is just 2. I plug it in, nothing funny happens, the function is perfectly defined there, f of 0 is equal to 2, and life is good. I would then ask myself, what happens when I plug in positive numbers? And I would just pick a few of them to kind of think through in my mind what happens here. Well, what happens if I plug in a 3 or a 5 or a 9 or a 200,000? Well, the answer is you plug those in, the function behaves perfectly okay, and you get out a number. So that is a non-issue. Let's talk then about what happens when I plug in negative numbers. Is it legal to plug in a -5 or a -200? And the answer is yes, it is. The function behaves okay and I get out a number. So what we see here is that our domain is all real numbers. Notice the R that is written there. If you're writing that R manually, it would look like this: R with a double bar. It's like a capital R, but it has that double bar written there. And that's how you can write all real numbers just in shorthand if you want to use that. Let's remind ourselves that the domain consists of the x's that you can plug in. Let's now talk about the range. The range are the y's that you get out. Well, if you plug in positive numbers, you get out positive numbers. If you plug in negative numbers, you get out negative numbers for the most part. And so what we see here is that the range is also all real numbers. Remember, these are the y's that you get out. Let's examine the graph of this function and see if we can talk about the domain and range by looking at it. Notice if we're talking about the domain, we're talking about the x values. So I would be asking myself, how far does this line extend to the left? Well, the answer is if I kept extending it, it continues infinitely far to the left. It also continues infinitely far to the right. Therefore, I can even see from my graph that the domain is all real numbers. When we look at the range, we ask ourselves, how far up and down does the graph extend? We'll look at it again. Let's start at the bottom. Here, how far down does that graph continue to go? To infinity. And how far up does it continue to go? To infinity. And so graphically, we can see that the range is all real numbers as well. Let's talk a little bit more now about domain. This time, let's take a function that is f of x is equal to 1 divided by x minus 4. I want to talk to you a little bit this morning about a hint that you need to remember every time you see a function that is written in the form of a fraction. Remember that fractions are undefined when the denominator is 0. Well, you may be able to tell by looking at this one, what number could I plug in right here that would make this denominator be 0? Think about that for just a second. What if I plugged a 4 right there? 4 minus 4 is 0 in the denominator. Well, that would be a problem area for us. Now, for those of you who said, I didn't quite see how you came up with that 4, there's another step you can do. For a lot of you, this step will be unnecessary, but if you have trouble seeing that, here's the step you can do. Take the denominator, set it equal to 0, and solve. So take the denominator, x minus 4, set it equal to 0, and solve. Add 4 to both sides, and I get x is equal to 4. That is the one number that will cause you problems in that denominator. Now, what does that tell us about our domain? It tells us that any other number I plug in is okay. The one number that causes me a problem is 4. So the domain is all real numbers except x cannot be equal to 4. I must show that that's the one number I need to leave out. Let's look at another problem, this time one that is a little bit more difficult, so you may need that in-between step. It's still a fraction, so the same hint still applies, and this time we have f of x is equal to 1 over 3x plus 4. This time we may need that extra step, so we do 3x plus 4 is equal to 0. Take the denominator and set it equal to 0 to find what value of x makes the denominator be 0. As we solve, we'll subtract 4 from both sides, and we get 3x is equal to a negative 4. Our next step is to divide both sides by 3, and so I get x is equal to a negative 4/3. Let me remind you, that is the one number that if I plugged it in right here, would give me a 0 in the denominator. So it's the one number that must be left out of the domain. How do you write that domain? The domain is equal to all real numbers except x cannot be equal to a negative 4/3. Now we're going to change tracks and we're going to look at another kind of problem that we need to talk about the domain for. This time we're going to be looking at square roots. Now, if you think with me about square roots, you should remember that there is no real number solution for square roots of negative numbers. So our problem area this time will be numbers that we plug in for x that would cause the radicand to become negative. Let's see if we can reason this one out, and then I'll show you the in-between step. First of all, what number could I plug in for x that would make the radicand equal to 0? Let's start by looking for that. Well, if I plugged in a 3 right here, I would have the square root of 3 minus 3, which is equal to the square root of 0, which is just 0. That's perfectly okay. Well, let's use that 3 as our jumping off spot, and this time we'll move to numbers that are larger than 3 and then smaller than 3. We should expect one group of those numbers to be okay and the other group to not be okay. So let's talk about what would happen if we chose a number that was larger than 3. For instance, let's do 4. Let's come right here and we'll do the square root of 4 minus 3. Well, that's equal to the square root of 1, which is just 1. Perfectly okay. What would happen if we did 5? Well, we would have the square root of 2. It's not a perfect square, but it's at least still the square root of a positive number, so that would be okay. What then would happen if we chose numbers that were smaller than 3? Let's continue looking at that. What if I did the square root of 2 minus 3 this time? Well, that would give me the square root of a negative 1, and that's a problem. So as soon as we hit that, we realize that numbers that are equal to 3 or greater than 3 are going to be okay. So how do we write that now in such a way that we can define our domain? We would say that our domain is equal to the set of all numbers such that x is greater than or equal to 3. Let's look at the graph now and see if we can also determine from the graph that the domain is x's that are greater than or equal to 3. Remember, the domain consists of the x values. So what we'll want to do is we'll want to look at our function from left to right and we'll want to say what x's are included in that function. Well, if you'll look way back out here, there are no x's included in that function here. That doesn't touch that red graph in any place. But when we arrive at 3, we now have a function. For 4, we have the function. For 5, we have a value of the function. For 6, we have a value of the function. For 7, do you notice all the way across there? How far could I continue on out here and have a value for that function? Well, the answer to that is infinitely far. So our domain are the x's that go all the way from 3 out to positive infinity. Next, we want to look at another function that has a square root, and this one may not be quite as easy to deal with. Remember, our hint is that we still cannot be taking square roots of negative numbers. This time, let's set that radicand equal to 0 so that we can figure out what the number is that will give us 0. When we solve, we get 2x is equal to a negative 3, so x is equal to a negative 3 over 2. That's the number that when you plug it in would give you the square root of 0, which is okay. Let's look then at numbers that are larger than negative 3 over 2 and smaller than negative 3 over 2. First of all, a number that is larger than negative 3 over 2 would be 0. Would you agree on a number line that it's to the right of negative 3 over 2? That would be a very easy one to plug in, so let's do that. If we took the square root of 2 times 0 plus 3, let me extend that radical over there, what we would get would be the square root of 3. Well, that's a positive number, so life is good. Well, what happens if we take numbers that are smaller than negative 3/2? For instance, negative 2. Let me remind you that negative 3/2 right here is nothing more than a negative 1.5. So that may help you in remembering what's larger than that and what's smaller than that. So if we're looking for a number that is smaller than a negative 1.5, let's move to a negative 2 and look at it. Well, if I took the square root of that, I would be doing 2 times negative 2 plus 3. That gives us the square root of negative 4 plus 3. So that's equal to the square root of a negative 1. And that's our no-no. We are not going to be able to take the square root of a negative number and end up with a real number solution. So that's the one we need to eliminate. What that tells us is that this number right here is okay, and any number larger than it. 0 would work, 1 would work, 400 would work. So any number larger than that. So how do we write that now in math? We say our domain is equal to the set of all x's such that x is greater than or equal to a negative 3/2. Let's look at the graph now and see if we can see from that graph how that's true. Here's the graph of the square root of 2x plus 3, and I want you to notice the x values. If you come out here, you see no x's involved, and all of a sudden when you get right here to a negative 1.5, the x values pick up, and from here all the way across infinitely far, you'll see that the function has a value that can pair with each of those x's. So the x's that are legal are the x's right here from a negative 1/2 all the way to positive infinity. So you can see that from the graph as well as from symbolically solving for it. Let's look now at how we can estimate a domain and range from a graph if that's all we have. Maybe we don't even have a function, but we have a picture of it. So let me give you this graph. This time what I'll be asking you is to estimate the domain and the range from the graph. When we estimate the domain from the graph, we're literally looking across that graph and we're saying what is the number that you see that is the farthest to the left and the number that you see that is the farthest to the right on the x-axis. So let's look across here. The place that is farthest left on our graph is right here, and it's when x is equal to a negative 2. The place that is the farthest to the right is right here, and it's when x is equal to 3. So that is exactly what your domain is. The domain consists of x's that are in between -2 and +3. Notice that this is always written with the small number on the left, the larger number on the right, x in the middle, and both symbols are always less than or equal to. Now we want to examine the range. To examine the range, we want to look at how far down and how far up the graph extends, this time on the y-axis. Let's begin with the smallest value. Well, on the y-axis, the smallest value I see right there corresponds to a 1. The y value is 1. And the highest value, the furthest up on the graph that I see, is right here, and it corresponds to a 3. So our range is right here. It's everything between 1 and 3. Well, to write that with a range, you write the set of all y's this time, since we're talking range. And it's the set of all y's such that 1 is less than or equal to y, which is less than or equal to 3. Notice again, you have the smallest number here, the larger number here, the y in the middle, and both symbols are less than or equal to. Let's do another one of these where the graph looks a little bit more complicated now. The process is the same. We still want to find the domain and the range. Once again, for the domain, I'm looking at how far to the left the x's extend and how far to the right do they go. Well, let's examine the picture. The furthest thing I see to the left is this point right here, and the x value there is a -2. The furthest thing I see to the right is right here, and the x value is a +2. So our domain are going to be the x's in between these two places right here and including them. So we have the set of all x's such that, notice that bar, I always say that, but I want to make sure that you remember that bar says such that. So I have the set of all x's such that -2 is less than or equal to x, which is less than or equal to 2. Once again, you'll notice the little number, the big number, x in the middle, and both symbols are less than or equal to. Let's now look at the range. In the range, remember, we look at how low does the function go and how high does it go. So what is the lowest place you see on this graph? Well, it's right here. And what is the highest place that you see on the graph? Right up here. Well, this low spot is right here at a -3, and the high spot is up here at 3. So our range is right there. It is the y's that are in between -3 and +3. How do we write that? The set of all y's such that -3 is less than or equal to y, which is less than or equal to 3. And I want to leave you today with a little R&R. You know, Remington at the river. See you next time. Bye-bye.